The Greeks don't explain everything. They are like the vital signs of a patient: heart rate, blood pressure, temperature. Useful, but they don't capture emotions, sudden shocks of rare events. Welcome to Financial Flywheel, where we encourage and support one another to design, nurture, and run your financial flywheel that can take you closer to financial freedom. Today, we will have a look at these Greeks and understand them in the context of nifty options. The same principles apply to global markets also, and their underlying of commodity, stocks, or index traded there. This discussion would come under the section of market analysis and tools. This knowledge will help us inch closer to gaining mastery on F&O. How to price option premium? Every trader today definitely owes a silent debt to three men who cracked the code of modern options: Fisher Black, Myron Scholes, and Robert Merton. Their formula didn't just price options, it changed Wall Street forever. Let's pay a tribute to the brilliance of Black Scholes and see how their work still shapes every move traders make today. Their work was appreciated through a Nobel Prize. Their model became the bedrock of derivatives markets, paving the way of trillions of dollars in global trade even today. Imagine if they had a royalty around it, they would have been the most richest people on this planet. It is because of Black-Scholes model, today we have clear articulation of what Greeks are. How to view significance of Greeks and look at probability distribution function? Let's take a lateral analogy. Greeks, which are delta, gamma, vega, theta, and rho, are like the blood pressure, pulse, oxygen levels, sugar levels. They are instant readings of how the body or option position is responding at this very moment. Standard deviation, on the other hand, captures something more subtle. These are like the 1 sigma moves, 2 sigma moves. They are vital, but more than a vital immediate action to be taken, they are more like a health risk assessment or a stress test, we can say. Of course, looking at standard deviation, we would take immediate action if the situation was critical. Otherwise, if the vital statistics are all right and the standard deviation also does not indicate an immediate attention or an action need to be taken, we might let the market play out. So in the human world, we can think of the standard deviation is something like a ECG treadmill test or a cholesterol profile. It doesn't tell you how you might feel right now, but gives you a probabilistic range of where risks could lie in the future. In the options world, for instance, uh, from where the market stands now, a 1 sigma move is the range of outcomes, maybe upwards or downwards, that are expected with a 68% probability over a given time. The time in this context can be the expiry of the contracts, which are there in play. It is the probable boundary around which our Greeks will operate. So, while Greeks answer, if the market twitches now, how does my position respond? The standard deviation could answer something like this: how much twitching should I reasonably expect? And what's the safe zone versus a danger zone? That's why traders look at both the Greeks for the present tense, the sigma and standard deviation, hence the moves of probability distribution for a futuristic and a projection of how things could evolve. Now let us imagine that we are driving up a hill. We will look at one aspect of the Greeks today, which is delta. And in a while, you will know what is the significance of driving a car versus delta. So the uphill slope tells us how much extra effort the car needs for each meter we move forward. Similarly, delta is the uphill slope or the option price with respect to the stock price. So the steeper the slope, the bigger the reaction to the market moves. In technical terminology, how much my option price will change if the underlying moves by 1 point. That is the technical definition. But if we want to visualize how it actually can play out, we can look at the car as a guidance in a slope, or we can also look at it in a probabilistic angle. For instance, a call with a delta of 0.7 means there's a 70% chance that the contract will expire in the money. The market will expire in the money within the contract. Similarly, put delta of minus 0.30 would mean a 30% chance that the contract will land up to be in the money. See, the sign of positive and negative sends some confusion amongst several, but let us take it like this. A positive delta means we are discussing calls, because call would inherently come into play when the market gains, and the negative connotes that of a put. So now we can, for the time being, just look at the magnitude and forget the parity of whether it is positive or negative, because they connote call and put respectively. Okay, now the magnitude in this particular example is 30%, 0.3, which means there's a 30% chance that the contract will become in the money, and call option of 0.7, 70% chance. Assume that both the contracts expire at the same period of time. Since the put option has a higher chance of landing up in the money, chances are the premium that the put option will charge will be greater than that of the call option. Now, when we look at the slope analogy, we find that the greater the difficulty it is for the car to drive and move 1 meter, the greater the difficulty would mean the probability of accomplishing that will be more difficult. And hence, in that context, it would have a higher slope and a lower probability. So these are all the mental models that one can use when one discusses the concept of delta in the Greeks. For, let us say, a Nifty option, which is in this particular case a put option, the learning is similar to call option, and hence there are no slides that we will discuss call option separately for today's discussion. What we notice in this slide is the current market price is 24,981. It is a contract of Nifty. In the left hand side you have a Nifty option that has 14 days to expire. In the right hand side you have Nifty option which has 9 days to expire, Nifty being the underlying. And we look at the same strike price, 24,800. 24,800 is lesser than 24,981. And hence, the market will have to fall for it to reach 24,800. Now you notice the premiums for the 9 days to expire, that is on 28th August, is 66.6, and that of 14 days to expire 2nd September is 96.4. The premium is greater for the one that has more time to expire. Next, we will now look at the delta. This screenshot was taken using a tool of Sensible, though we have several other tools like Opstra which could also give us the same information. We have similar tools for the US also, but they don't come out of the box. We would have to sign up for those brokers, and then you would get either in Tasty Treats or in First Trade for us to look at these values. Okay, so the delta for the 9 days to expire is minus 0.27, and that of 14 days to expire is minus 0.3. We already told that minus, we can put it aside, it just means it's a put option. 0.27 is lesser than 0.3 because the chances of the contract with the lesser number of days to expire in the money is lesser than the same strike price with a contract having more days to expire. This explains the reason why the delta is lesser in magnitude for the 9 days to expire compared to 14 days. Now let us take another example, but this time the contract is in the money. See, 24,981 is the strike price. Now let us take 25,200. 25,200 put option, if you notice, it is much greater strike price compared to 24,981, which means that as of now, the contract is in the money. The negative sign of delta means it is a put option. So that we will ignore for the time being. Now let us look at the premiums. The 9 days to expire is 241.75 and that of 14 days to expire is 264. The number of days are more for the 14 days to expire compared to that of 9 days. That is one argument. The next argument is, which is again very strange at this point in time, is if you notice, the 9 days to expire has a higher delta of 0.67 compared to 14 days to expire delta of 0.6. Why is that so? The reason being, if we have 9 days, then the chance for this contract moving from in the money to out of the money is 0.67 times, say 0.67. That is the capture. However, for 14 days, for the contract to move from in the money to that of out of the money is 0.6. It has a greater chance. The negative, because it's negative to minus 0.6, it is a greater value compared to that of minus 0.67, isn't it? And hence, the odds are higher that the contract can move out of the money for a 14-day contract compared to 9-day contract. So this explains why the magnitude is greater for a 9-day contract compared to that of a 14-day contract. Now let us summarize what we discussed today. Today we got ourselves introduced to the Greek names and covered one delta, one concept of Greek called delta. Delta is the probability of a contract expiring in the money. More time means more chance for out of the money to become in the money. But for in the money options, more time can reduce the delta slightly because there's a chance they could be slipping out of the in the moneyness. We did not discuss at the money because we did not find the right scenario. But we can understand this, that at the money options, if the spot price is same as the strike price, that is, both near and far expiry will be hovering around 0.5. But longer expiry deltas are more stable. That should be our takeaway. The reason being, the chance of a lower expiry contract, the chances of it to shuttle between in the moneyness to out the moneyness will be very swift as the market moves around the at the money range. And hence, there is a huge fluctuation. It will be choppy. But if the number of days to expire is more, then what happens is this choppiness is lesser. However, the value of the delta will be around 0.5. Okay, these concepts will remain the same irrespective of the underlying, and these values constantly change basing on the market movements. Again, mind you, they tell us how the vitals are at this point in time. We can't look at the Greeks only in isolation. We would need to club it with the probability distribution function and our strategies uh, when the model is tested, so that we can make adjustments or add and take certain positions whenever there is an increased drawdown. We will cover more of the Greeks in the days to come to help us assess the just in time vitals better. Thank you for your time. Good luck for all that you're doing. Until we meet next, bye for now.